Welcome to my little corner of the internet, where we celebrate creativity and growth. Welcome to another exciting video, where we'll be shedding light on Kobayashi metric. In mathematics and especially complex geometry, the Kobayashi metric is a pseudometric intrinsically associated to any complex manifold. It was introduced by Shoshichi Kobayashi in 1967. Kobayashi hyperbolic manifolds are an important class of complex manifolds, defined by the property that the Kobayashi pseudometric is a metric. Kobayashi hyperbolicity of a complex manifold X implies that every holomorphic map from the complex line Celsius to X is constant. Get ready for an enlightening exploration as we dig into definition and understand its role in the broader context. The origins of the concept lie in Schwarz's lemma in complex analysis. Namely, if f is a holomorphic function on the open unit disk D in the complex numbers Celsius such that f equals 0 and f's 1 for all z in D, then the derivative f0 has absolute value at most 1. More generally, for any holomorphic map f from D to itself not necessarily sending 0 to 0, there is a more complicated upper bound for the derivative of f at any point of D. However, the bound has a simple formulation in terms of the Poincare metric, which is a complete Riemannian metric on D with curvature isometric to the hyperbolic plane. Namely, every holomorphic map from D to itself is distance decreasing with respect to the Poincare metric on D. This is the beginning of a strong connection between complex analysis and the geometry of negative curvature. For any complex space X, for example a complex manifold, the Kobayashi pseudometric dx is defined as the largest pseudometric on X such that dxfax phi x, y, for all holomorphic maps f from the unit disk D to X, where x, y denotes distance in the Poincare metric on D. In a sense, this formula generalizes Schwarz's lemma to all complex spaces, but it may be vacuous in the sense that the Kobayashi pseudometric dx may be identically 0. For example, it is identically 0 when x is the complex line Celsius. This occurs because Celsius contains arbitrarily big disks, the images of the holomorphic maps f are d Celsius given by th equal as for arbitrarily big positive numbers a. A complex space X is said to be Kobayashi hyperbolic if the Kobayashi pseudometric dx is a metric, meaning that dx is 0 for all x, y in X. Informally, this means that there is a genuine bound on the size of disks mapping holomorphically into X. In these terms, Schwarz's lemma says that the unit disk D is Kobayashi hyperbolic, and more precisely that the Kobayashi metric on D is exactly the Poincare metric. The theory becomes more interesting as more examples of Kobayashi hyperbolic manifolds are found. For a Kobayashi hyperbolic manifold X, the Kobayashi metric is a metric intrinsically determined by the complex structure of X. It is not at all clear that this should ever happen. A real manifold of positive dimension never has an intrinsic metric in this sense, because its diffeomorphism group is too big to allow that. Welcome to the next segment, where we explore examples and its significance in our journey. 1. Every holomorphic map f, x, y of complex spaces is distance decreasing with respect to the Kobayashi pseudometrics of x and y. It follows that if 2 points p and q in a complex space y can be connected by a chain of holomorphic maps Celsius y, then d equals 0, using that dc is identically 0. This gives many examples of complex manifolds for which the Kobayashi pseudometric is identically 0, the complex projective lines, or more generally complex projective space span, using the exponential function Celsius, an elliptic curve, or more generally a compact complex torus. 2. Kobayashi hyperbolicity is preserved under passage to open subsets or to closed complex subspaces. It follows, for example, that any bounded domain in Kin is hyperbolic. 3. A complex space is Kobayashi hyperbolic if and only if its universal covering space is Kobayashi hyperbolic. This gives many examples of hyperbolic complex curves, since the uniformization theorem shows that most complex curves, also called Riemann surfaces, have universal cover isomorphic to the disk D. In particular, every compact complex curve of genus at least 2 is hyperbolic, as is the complement of 2 or more points in C. As we venture forward, let's take a closer look at basic results and its impact on our understanding. For a Kobayashi hyperbolic space X, every holomorphic map Celsius X is constant, by the distance decreasing property of the Kobayashi pseudometric. This is often the most important consequence of hyperbolicity. For example, the fact that Celsius minus 2 points is hyperbolic implies Picard's theorem that the image of any non-constant entire function Celsius misses at most 1 point of Celsius. Never-linear theory is a more quantitative descendant of Picard's theorem. Brody's theorem says that a compact complex space X is Kobayashi hyperbolic if and only if every holomorphic map Celsius X is constant. An application is that hyperbolicity is an open condition in the Euclidean topology for families of compact complex spaces. Mark Green used Brody's argument to characterize hyperbolicity for closed complex subspaces X of a compact complex torus. X is hyperbolic if and only if it contains no translatable positive dimensional subtorus. If a complex manifold X has a Hermitian metric with holomorphic sectional curvature bounded above by a negative constant, then X is Kobayashi hyperbolic. In dimension 1, this is called the Alpha-Schwarz lemma. With our foundation established, it's time to explore the Green-Griffiths-Lang conjecture and its relevance to our overarching theme. The results above give a complete description of which complex manifolds are Kobayashi hyperbolic in complex dimension 1. The picture is less clear in higher dimensions. A central open problem is the Green-Griffiths-Lang conjecture. If X is a complex projective variety of general type, then there should be a closed algebraic subset Y not equal to X such that every non-constant holomorphic map Celsius X maps into Y. Clemens and Vizan showed that for n at least 2, a very general hyperspace X in spin of degree d at least and has the property that every closed subvariety of X is of general type. Very general means that the property holds for all hyperspace of degree d outside a countable union of lower dimensional algebraic subsets of the projected space of all such hyperspace. As a result, the Green-Griffiths-Lang conjecture would imply that a very general hyperspace of degree at least n is Kobayashi hyperbolic. Note that one cannot expect all smooth hyperspace of a given degree to be hyperbolic, for example because some hyperspace contain lines isomorphic to sp. Such examples show the need for the subset Y in the Green-Griffiths-Lang conjecture. The conjecture on hyperbolicity is known for hyperspace of high enough degree, thanks to a series of advances by Siu, Demely and others, using the technique of jet differentials. For example, Deverio, Mercer and Rousseau showed that a general hyperspace in spin of degree at least n satisfies the Green-Griffiths-Lang conjecture. General means that this holds for all hyperspace of given degree outside a finite union of lower dimensional algebraic subsets of the projective space of all such hyperspace. In 2016, Brodbeck gave a proof of the Kobayashi conjecture for the hyperbolicity of general hyperspace of high degree, based on a use of Wronskian differential equations. Explicit degree bounds have then been obtained in arbitrary dimension by Yodeng and Demely, e.g. by the latter. Better bounds for the degree are known in low dimensions. McQuillan proved the Green-Griffiths-Lang conjecture for every complex projective surface of general type whose Chern numbers satisfy KIK. For an arbitrary variety X of general type, Demey showed that every holomorphic map Cx satisfies some, in fact, many algebraic differential equations. In the opposite direction, Kobayashi conjectured that the Kobayashi pseudometric is identically zero for Calabi manifolds. This is true in the case of surfaces, using that every projective surface is covered by a family of elliptic curves. More generally, Campana gave a precise conjecture about which complex projective varieties X have Kobayashi pseudometric equal to 0. Namely, this should be equivalent to X being special in the sense that X has no rational fibration over a positive dimensional orbifold of general type. Let's now shift gears and explore analogy with number theory through a critical lens, uncovering its strengths and weaknesses. For a projective variety X, the study of holomorphic maps Celsius X has some analogy with the study of rational points of X, a central topic of number theory. There are several conjectures on the relation between these two subjects. In particular, let X be a projective variety over a number field K fix an embedding of K into Celsius. Then Lang conjectured that the complex manifold Xi is Kobayashi hyperbolic if and only if X has only finitely many F rational points for every finite extension field Fahrenheit of K. This is consistent with the known results on rational points, notably Falting's theorem on subvarieties of abelian varieties. More precisely, let X be a projective variety of general type over a number field K. Let the exceptional set Y be the Zariski closure of the union of the images of all non-constant holomorphic maps Celsius X. According to the Green-Griffiths-Lang conjecture, Y should be a proper closed subset of X and, in particular, not be equal to X. The strong Lang conjecture predicts that Y is defined over K and that XY has only finitely many F rational points for every finite extension field Fahrenheit of K. In the same spirit, for a projective variety X over a number field K, or, more generally, a finitely generated field K of characteristics 0, Tampana conjectured that the Kobayashi pseudometric of Xi is identically 0 if and only if X has potentially dense rational points, meaning that there is a finite extension field Fahrenheit of K such that the set Xi of F rational points is Zariski dense in X. In this section, we'll be peeling back the layers of variance to reveal its true essence. The Kobayashi is another intrinsic pseudometric on complex manifolds, based on holomorphic maps to the unit disk rather than from the unit disk. The Kobayashi infinitesimal pseudometric is a Finsler pseudometric whose associated distance function is the Kobayashi pseudometric as defined above. The Kobayashi-Eisenman pseudo-volume form is an intrinsic measure on a complex n-fold, based on holomorphic maps from the n-dimensional polydisk to X. It is understood better than the Kobayashi pseudometric. In particular, every projective variety of general type is measure hyperbolic, meaning that the Kobayashi-Eisenman pseudo-volume form is positive outside a lower dimensional algebraic subset. Analogous pseudometrics have been considered for flat affine and projective structures, as well as for more general projective connections and conformal connections. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.